Okay, so today we are going over section 5.1, which is our last lesson of this course. Then on Wednesday, I plan to review, and Monday is test 4. And then we have Thanksgiving break. We come back and we just review and final exam. So, the end is so close, we can taste it. I'd really like to be able to pull up Blackboard and talk a little bit about what we're doing for the test, because it's going to be a little different than what we've done before. I don't know if you've kind of seen that. You've been looking ahead. We're just going to do one version of the test. Everybody will get the open book take-home test. There are parts to go with it where you have to watch a video. We've watched some videos in here. We watched the where he does 75% of the dollar bill and you see it getting smaller and smaller. We did the graphing stories where you had to graph how much water was in the container, or how high was his waist, that kind of thing. You'll have some videos to watch as part of the test. They will most likely be like those kinds of things. I think I referred to that video about the turtles on the islands. I think I have a question about that, so you could re-watch that video if you needed to remember what was going on. Okay, we are updated. Let's see if I can log in. Nope, that's not it. Okay, it's logging in. Great. So, on our test day, I will show those videos here, and you can work on the test here. The benefit of that would be if you didn't understand a question or something, it's real easy to ask instead of sending me an email. But you're not, and if you wanted to, you could just leave the test with me and you don't have to upload it. If you wanted to get started on the test early and just hand it in on that day, you can. Or if you're in here, you're working on it, and you're like, I need more time on this, I need to take it home, and I'll just upload it on Blackboard. You can do that too. So, coming to class that day does not hurt your abilities at all to be using your book or your notes or having extra time. I don't believe I made a practice test for you this time. I figure since you're getting to look at the take-home test, maybe you don't need a practice test. It will be available. I really want to pull a Blackboard so I can remind myself when it's available. I think I made it available this Wednesday. So after class, I think it pops up during class. So as soon as we're done Wednesday, you could, I think, pull up the real test and look at it. The one thing that I'll say is, on the day of our test, I'm not going to be willing to answer questions like, I don't remember how to do this. So, once the test is out, it's kind of, hope you knew it. super slow. Maybe we'll pull it up at the end. Okay, so let's learn about ratios and proportions. This is section 5.1. Okay, we're maybe getting there. It's just fast enough that it lures me back to try to pull it up. Okay, so let me get this thing to look like yours. Okay, so what you have due Wednesday is the stuff from today. Not a lot. And then I just put this up here, review day 11/18/20, just to kind of, I don't know. I don't have a folder of new things that are due on the 18th, I guess. Like there's no prep work, it's just all the stuff from today. It's due on the 18th. So then on the 18th, we'll review, and then, okay. So then on the 18th, the test will become available. So in this folder, which I believe if we open it, it'll be empty right now. Yeah. Okay, so on Wednesday the 18th, test will show up in this folder, and it will be due on Tuesday, the 24th. So we meet the 23rd in class, and we can be working on the test. I'll play the videos, anything. Hopefully anything you need the internet for, we can make happen here. You can leave it with me, or you can take it home and turn it in that day or the next day. And then you'll have Thanksgiving break, and you'll come back for the final. So not a lot of stuff to do over Thanksgiving break, other than if you have anything that you didn't get turned in from this chapter. I guess you could be working on that. I'll give you a hard copy of the test on Monday. So if there are things that you need to graph or something that you'd like to have the actual paper to work on, you could, get started on it and staple your work to that test if you want to do that, if you don't have a printer or something like that. Any questions about the test? You can email me if you think of more. Great, okay, so ratios and proportions. Okay, so I'm just at the top of page 475. The most obvious way to compare the sizes of two numbers is to subtract them. But is that the best way? Suppose you're comparing the cost of an item at two different stores, and you find that the item is $1 more at Target than at Walmart. If that item is a bottle of Coke, and the prices are $1 and $2, that dollar difference is significant. You'd most likely feel pretty strongly about buying from the cheaper store. But if the item is a 60-inch flat-screen TV, and the prices are $1,201 and $1,200, would you really care? Those two prices are essentially the same, it's just $1 difference, but that difference just feels inconsequential. If you divide the prices rather than subtract them, something interesting happens. So we see it right there. For the bottles of Coke, $2 divided by $1 is 2. One of them is twice as much as the other, 2 times. If we take the TVs, we get 1.0008. One of them is 1.0008 times as big. Do you see the point? For the Coke, $1 more is twice as much, kind of a big deal. For the TV, when you divide the prices, you basically get 1, meaning the two prices are pretty much the same. Conclusion, the most meaningful way to compare the sizes of two numbers is to divide them, forming what we call a ratio. The study of ratios as a means of comparing numbers will lead us into a type of equation that can be used in a lot of modeling situations, the proportion. So then in that class section, ratios. A ratio is a comparison of two quantities using division. For example, according to a 2015 survey reported in the New York Daily News, for every 76 people that reported some religious affiliation, there were 24 that did not. We would say that the ratio of those with an affiliation to those without is 76 to 24. So notice that in the sentence, we would say that the ratio of those with an affiliation, the thing that's listed first, is also the first number. The ratio of those with an affiliation to those without, that number is the second number. So 76 to 24. We wouldn't say 24 to 76 unless we switched the descriptions in the sentence as well. So the order that it's in the sentence is the order that you put the numbers. Think of like teacher to student ratio. If it was teacher to student ratio, you'd put the number of teachers first and the students second. If it's student to teacher ratio, you put the number of students first and the teachers second. Ratios are typically written in two different ways, using a colon between the quantities or in fractional form. So we could write the ratio in the previous paragraph as either 76, at colon we would say 2 when we're reading it, 76 to 24, or 76 over 24. If you're writing it with a colon or with the word 2, left to right, it goes the same order as what you said in the sentence. If it's a fraction, the first one that's mentioned is the one that goes on top. So once again, teacher to student ratio, teacher would go on top, students go on bottom. If it was student to teacher ratio, then students would go on top and teachers would go on bottom. Page 476. In this course, we'll mostly use fractional form so we can do arithmetic and algebra with ratios. Notice that if you perform the division in the ratio 76 over 24, you get about 3.2 in decimal form, rounded to one decimal place. This shows us that there are a little more than 3 times as many Americans that have a religious affiliation as those who do not. And this brings us full circle on what the point of ratios is, comparing sizes of quantities. So, number 1. From 1969 through 1977, 4 of the teams in Major League Baseball made the playoffs each year, while 20 did not. Now, 10 make the playoffs and 20 do not. Write the ratio of teams making the playoffs to the total number of teams in 1969 and today. Write each ratio in fractional form, then reduce the fraction if you can. Where's my black? There it is. Okay, so this is page 476, number 1. In 1969, we want to make a fraction, and then today, we're going to make a fraction. So, the ratio of teams making the playoffs, that's the first thing listed, so playoffs goes on top, to the total number of teams, that goes on bottom. We could also do a ratio of the total making the playoffs to those that don't make the playoffs, which would be a different number. So just pay attention to what it actually is saying. Kind of reminds me of probability versus odds. You know, are we putting the total on the bottom? Are we making those that aren't on the bottom? Just need to make sure we read what it says. So in 1969, we had 4 that made it, 24 that didn't. Today, 10 make it. Oh, sorry, out of 24. 10 make it out of 20. 20 total, 24 total. Number 2, describe what those ratios tell us about how likely a given team is to make the playoffs now as compared to in the mid-70s. So maybe you're really comfortable with fractions. You have a good sense of how big 4 24ths is and how big 10 20ths is. These are definitely mathematically accurate things, but we could reduce these fractions. 4 24ths is the same as 1/6, and this is the same as 1/2. Oh wait. This is wrong. This is not the total. I am so sorry. That's what I get for not really reading it. Yes, we want making the playoffs to the total. 20 did not, so 10 did, total of 30. Yep. Did you all catch that and you were just confused?
Yes.
What's she doing? She's making such a big deal about it should be total and she's not writing that. All right, there we go. So maybe this is a little more obvious. Oh, well, they're twice as likely to be in the playoffs, all things being equal, than they used to be. We could also come up with a decimal. That would also maybe make it easier to compare. Number 3, why was it useful to reduce the ratios? It just helps us. Sometimes if we reduce it, makes it easier to compare those numbers. So there's a skill that we want to have. We want to be able to compare ratios. In order to do this, here are the steps. Step 1. Just set it up as fractions, just like we did. Step 2, actually compare them. This is so complicated, isn't it?
Is this number 5?
No, this is just
No.
me talking, yeah. I have it written in my book underneath number 3 because that's when I like to write it on the board. When you're comparing these two, there's a couple different strategies you might want to use. You could use fraction arithmetic. That's what they're encouraging you to do in the text. They're saying, reduce these fractions, and that makes it easier to compare 1/6 versus 1/3. But sometimes you reduce the fractions and you end up with something like, I don't know, 5/6 and 33/35. And maybe that isn't quite as obvious how those two compare. Sometimes when you reduce the fractions, it's still kind of hard. So Your other option is that you could convert it to a decimal. So you, on your calculator you do 4 divided by 24, 10 divided by 30, and you get two numbers, and it's really easy to see which one's bigger, which one's smaller. That's the second option. Number 4 talks about a sub shop with an 18-inch sandwich, and another one that has a 2-foot long sandwich. And then they wrote this ratio for you, 2/18. What's wrong with that?
It's supposed to be 18/2.
You're right, the 18 one is listed first. So yes, especially if they were to say, what's the ratio of the 18-inch sandwich with the 2-foot long sandwich? Then yeah, you'd want to put that one first. There's something else that is glaringly wrong.
Reducing.
I would say the inch to the foot.
That's what I'm looking for. Comparing 2 feet with 18 inches, they don't have inches or feet in that fraction. If you're comparing 2 to 18, 2 looks like it's much smaller than 18. It looks like, oh, one of them is 1/9 the size of the other. But actually, the 2-foot one is longer. So number 5 is prompting us to fix that problem. If you wanted to fix the unit problem, instead of 2 and 18, what two numbers should you be using? We actually have a couple of options. If we wanted to put it in inches, what two numbers would we want to use? We've got an 18-inch sandwich and a 2-foot sandwich. How many inches is the 2-foot sandwich?
24.
So if we wanted to write a ratio that was meaningful, then we'd want to use the numbers 18 and 24. We'd want it all to be in inches. Or we could put it all in feet. If we put it all in feet, then we would have 2 feet, and how many feet is 18 inches? 1.5. So like 1.5. Now really, it kind of goes against the grain. I hope it goes against the grain. To put a decimal in a fraction. So if you were to write that 2 over 1.5, or if you're doing it in the other order, 1.5 over 2, you'd probably want to multiply by, like same numerator and the denominator, a fancy one, in order to get rid of that fraction. So maybe you could multiply it by like 2, you'd have 4 over 3, something like that. Okay. So, problems like these it's not really a problem, I'll say questions. Are all about comparing amounts using ratios. questions like, which is bigger? Or, are they the same? Or, how many times bigger? Or smaller. Sometimes we might just be looking at one ratio, like comparing the two sub sandwiches, or the two prices of Coke, or the two prices of the TV. Maybe we're comparing two ratios, like these two baseball teams, or baseball rules. Which playoff setup means that any given person's team is more likely to make it? Sometimes, other types of questions assume two ratios are the same and use that. We're using this idea of things being proportional. So we're gonna spend most of our time doing this kind of thing. And once we've done a whole bunch of this, and you get a question that's more like this stuff, you might try to set it up like this, and it doesn't work because it's not this type of question, it's this kind of question. So let's just put a bookmark in this and know some of the questions are like this. They're not all going to be like what we're going to spend most of our time doing. All right. So on page 477, we have a nice definition. A proportion is an equation stating that two ratios are equal. So we've got some sort of fraction equals another fraction. Fraction equals fraction. So something here, something here, something here, something here. In some cases involving only numbers, a proportion can be obviously true. For example, we most likely know that the ratios 1 to 2 and 4 to 8 are identical. If something occurs 4 out of every 8 times, that's the same thing as saying it occurs 1 out of every 2 times. In other words, 1/2 equals 4/8. This is a simple example of a proportion that happens to be true. If we know we have a proportion, we know two ratios are equal, but we're missing a piece of info. So this is a skill that you need. Here we go. Suppose you know two ratios are equal, but are missing one of the numbers. Find it. So for example, I have written as my example. something like this. I know these two fractions are equal because there's an equal sign right there. 1/2 equals something out of 8. Now this is 4, right? We just talked about that. We know it. But if we see something set up like this, how do we find x? So if I didn't know that it was 4, how would I find 4? I'm going to have to use some algebra. One method would be to multiply both sides by 8. You get 8 over 2 equals x, which is the same thing as 4. Another option is something that I have found most students love. They love cross multiplying. Do you love cross multiplying? I don't know what it is, but cross multiplying is like, we just have an affinity for it. We just love it. You take the 1 times the 8 and the 2 times the x, and then we divide both sides by 2, and we get 4 equals x. I don't know if you can see that. So let's just review. When can I cross, I'm going to put a little heart in there because everybody loves it. Cross multiply. You can cross multiply when you have fraction equal fraction. If you have fraction plus fraction, no. Just because you see two fractions, don't automatically cross multiply. If you have 1/2 plus x over 8, that is an addition problem. It is not a proportion. You cannot cross multiply with fraction plus fraction. You need common denominators, then you add across the top. You also cannot cross multiply if you do have an equal in it, but its fraction equals something else. Like if you had fraction plus something. Maybe I'll write that instead. Where's my eraser? Okay, I don't know if you can see that. I'm so sorry. I'll just say this out loud. You can cross multiply when it's fraction equals fraction. If this is a plus instead of an equals, no. If you have plus something else on one side or both, no. You can only cross multiply when it's fraction equals fraction. When cross multiplying is on the table, it's like, that's all we want to do. So, only use it when you can. Let me get this for our PDF here. So if you flip the page to page 478, we see, what is that, 12 over 60. Equals 3 over y. So we have fraction equals fraction. We can cross multiply. I can do 12 times y equals 3 times 60. If you don't like cross multiplying and you want to approach it more like this, then you'd have to multiply both sides times y. It would cancel with that y. And then you'd multiply both sides by 60, and it would cancel that 60. I guess you could reduce that first if you wanted. But what you're doing by multiplying both sides by y and then multiplying both sides by 60, you end up with this. Cross multiplying is just doing that all in one step. So then we divide both sides by 12. Oh, I don't know, what is that?
15.
Great. Okay, so the rest of the page, they're talking about all this cross multiplying business. Let's move on to an actual example. So we're going to start on all these problems on your 5-1 group section streamlined handout. The first question comes from page 480. The second question comes from page 481. I think the third question, I don't know where it comes from. I have to keep turning. Maybe you don't have. How many questions do you have on that thing? So 3? In the book, they walk you through step by step. Here we go. Okay, so it's 2 examples. They walk you through step by step, but you don't have to do it the way that they set it up. And sometimes I think that can be more confusing if a different setup makes more sense to you. So I'd prefer to leave our options open. So 5-1 group section streamlined. Previous years, I just had people like highlight the questions we were doing, and I was like, oh, just use the space in there to like fit your work in. But that just seems more chaotic to me. Why not just have a blank page, right? So our first example is about the spring break. Spring break road trip. They burn 12 gallons of gas in the first 228 miles. They refuel. They have 380 miles yet to drive and a 21-gallon tank. Can they make it without refueling again? So my first question is, what is the proportion that we're talking about here? I'm missing one piece of information. This is going to be one of those deals where I have a fraction equals a fraction, and one of the things I'm looking for, I'm missing. It's the same vehicle. So the amount of gas that vehicle uses on highway miles during the first part should be proportional to the amount of gas it uses on the rest of the highway miles. Same vehicle, same highway, or same type of driving, should be proportional. So I want, this is what I'm aiming for, something that's set up like this. The two amounts that we're going to be comparing are gallons and miles, right? I mean, essentially, we're looking at the fuel efficiency of this vehicle and using that to help us figure out how much gas it's going to take them for the rest of the trip. So we've got part 1 of the trip, we've got part 2 of the trip, gallons and miles. We have some options. I'm going to give you all 3 options. Could say, well, it took them 12 gallons to go 228 miles. How many gallons is it going to take them to go 380 miles? How many gallons do they need? Are they going to get that many out of a 21-gallon tank? That's one way. We could set up the problem and solve it. We could say, well, once again, took 12 gallons to go 228 miles. They refilled their tank, so they have 21 gallons. How far can they get on that 21 gallons? We can figure out how far they can get on 21 gallons, then we can say, oh, so does that swallow up that 380 miles they need? Or we could say, well, it took them 12 gallons to go 228 miles. If 21 gallons took them 308, so we're comparing fuel efficiencies. If their van has this miles per gallon, or gallons per mile, what they need to have happen is to be able to go 21 gallons to get them 380 miles. And then our question is this equal? Is it less than? Is it greater than? This setup is like the first set of problems we did on this board, where we were comparing like the major league teams in the past, the major league teams today. How do those two fractions compare? With that question, it was just, we could ask questions like, oh, is it more likely or less likely? And that's pretty obvious by looking at those two fractions, which way we want to go. But here, I would venture to say that most of you would have to think for a little bit, I know I would, if I took this fraction down to a decimal, and I took this fraction down to a decimal, and I knew for sure which one was bigger, I would still have to think for a while to figure out what the answer to the question was. Can they make it 380 miles without refueling? Even if I knew which fraction was bigger, I'd still have to think a little bit to actually translate it into this problem. I think this is the hardest way to go about this problem. You might do the math and figure out if they're equal or less than or greater than. If they're equal, then that's pretty obvious. But if one's bigger than the other, you might do that correctly and still answer the question wrong because you haven't interpreted your results right. That's tricky. With these, I think the transition between finding x and y and actually answering the question is easier. I would recommend you do it one of these two ways. So, which one do you want to do?
The first one.
Okay. Pink marker does not erase well. Okay, so if we go with the first one. So in this case, x equals how many gallons it takes for their car to go 380 miles, right? So if I cross multiply, $12 times 380. Now, if I included my units here, I'm going to get the same thing on both sides. Since I have the same thing on both sides, I can just kind of cancel them out. Be like dividing both sides by the same thing. Oh, I forgot my x. Whoops. There we go. And we'll divide both sides by 228. So, it takes 20 gallons, going back to what x is, to go 380 miles. So, to answer the question, can they make it without refueling? What do you think?
Because they need 21, right?
Their gas tank is 21 gallons. They refill it, so they have 21 gallons. They need 20 gallons. So think, you have $21 and you're trying to purchase something that's $20. Can you afford it?
No.
Yes. If we had set it up like this, we'd end up with a number of miles. We'd end up with how many miles can they drive on 21 gallons? And now we know, oh, well, it'd be something bigger than 380. So they can go further than they need. So we'd still get the same answer, just be a different route. Okay, page 484. Talks about the rule of matching parts. Rule of matching parts says that if you set up a proportion, you should be able to make a chart out of it. So, this one, this was set up correctly. We could make a chart out of that. There's the row of the gallons. There's the row of miles. This column is the first part of the trip. This column is the second part of the trip. You see how both of these amounts were part of the first trip, first half? Not half, but. In this column, this number is the number of gallons that they're going to use on the second part of the trip, and this is the number of miles that the second part of the trip is. These are both about the second part of the trip. This column, these are both gallon amounts of gas they're putting in their car, and these are both the amount of miles that they drive. This one's a little different, but it still works. Once again, I have gallons and miles. Both of these are gallon amounts. Both of these are mile amounts. This is what their car has done. This is what their car can do. So their car used 12 gallons to go 228 miles. Here, if there's 21 gallons in their car, here's how far they could drive. You could potentially call this first part of the trip and second part of the trip, but they're not necessarily going to use all 21 gallons. So that's why I kind of tweaked that column. This is, if they wanted to drive until they ran out of gas, here's how much gas they would use, and here's how far they could get. Both of these are the same thing. 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 If you wanted to, you could flip-flop these. You could put the miles on top and the gallons on the bottom. And it would still work. As long as you didn't just flip one of them. If you flip one of them, then it doesn't match anymore, because then you have gallons, miles, and miles, gallons. So there's a lot of ways you can set this up. Just make sure that you're consistent. Things are stacked vertically in categories, and things are stacked horizontally in categories. Okay, let's talk about the, okay, let's summarize. How do you recognize that it is a proportion problem? How do you do a proportion problem? Let's answer the how do you do a proportion problem question first. I think that one's easier. What do we do?
You can cross multiply.
Mm-hmm. Yeah, you set it up. Make sure you set it up right, so that the, could be made into a chart. And then you cross multiply. Easy peasy. How do you recognize if you're taking a test and there's a question? We've been doing mathematical modeling this whole chapter. How do you know the question isn't something about a linear equation versus a proportion problem? This is a harder question because there's only one key word I can think of, and that's proportional. If it happens to say two things are proportional, then you know, okay, this is a proportion problem. But it might not say that. This gas and miles problem didn't say that. Even if it doesn't say two things are proportional, you could ask yourself that question. Are we talking about something that's proportional? Like, you're talking about TV sizes. A standard, like, movie screen size or a standard TV size. You would think, I don't know that much about TVs. I'm assuming that they're proportional. If a TV is a certain width and you know how high it is, actually, this is a real life problem. My husband just did this. He knew what proportions are normal. Like, TVs are measured in the diagonal. So if they say this is a 60-inch TV, that means it's 60 inches across. So he apparently knew the ratio of the diagonal line to how wide it was. And he wanted to know what the biggest TV you could buy for how wide he had on the wall. So it's proportional. Like TVs are proportional in size. They might be bigger or smaller, but the diagonal relationship to how wide it is proportional. So if he knows, oh, well, for this size of diagonal, it's this wide, and I know how wide I want it to be, how big can my diagonal be? That's 4 pieces of information, and you're missing one. And you've got this relationship is the same as this relationship. That's a proportional problem. I think that whole paragraph that I told you is probably hard to just all copy verbatim onto your worksheet. But whatever makes sense to you. And then now let's look at the second example. This is from page 481. They have it all subdivided into steps. If you wanted to use those steps that they give you, you could. But keep in mind, the steps they give you, they're choosing a certain way to set it up. Like, I could have said, oh, we are doing this problem this way, right here. And you might think, I guess that's the only way to do it. So you could do it the way the book has it. But just like there were more than one option for this problem, there's more than one option for this example as well. I don't want to do the whole problem, but I want to kind of make sure we know how to set it up. So they've got this lake. And there's a whole bunch of fish. What do they want to know ultimately?
How many fish live in the lake?
So they caught a certain number of fish and tagged them. I don't know how you tag a fish. Put a little red mark. So they caught a certain number of fish, they tagged them, and put them back in. Let's see, just to make this. So then they put them back in the pond, they let them all swim around and get mixed up, and then they catch some more fish. And they look and see how many are tagged. So the assumption that they're making, it's like they're sampling from our last chapter. They're assuming that the sample they caught the second time has the same proportion of tagged fish as the entire population. sense? Now thinking back to our statistics and sampling lesson, is this a representative sample? Like that second catch that they got, does that really represent the whole pond? They're assuming it does. Maybe some fish are easier to catch than others, like some fish are just more dumb than others, I don't know. Like, are there the wily fish that never get caught? Are they more likely to catch the fish they caught the first time? Those are good questions that we might want to pose if this was in the sampling lesson. But we're just assuming that nope, all fish are equally likely to get caught. We're going to assume, it's not how you spell assumption, assumption, good grief. We're going to assume that in this second catch, the proportion of tagged to total is the same as in the entire lake. So what we know how many are tagged in the whole lake. We know how many are tagged in the second catch. And we know how many they caught total in the second catch. Do you see our 4 pieces of information here? We know how many are tagged in the whole lake, because that's how many they caught and tagged and then put back in. We want to know how many total are in the lake. So if we know how many are tagged in the whole lake, we want to know how many total there are in the whole lake. That should be proportional to how many are tagged in the second catch compared to the total they caught in the second catch. Now, does this problem say that it's a proportion problem? No. We have to take that extra step of looking and seeing, okay, is there some sort of proportional relationship here? This assumption that they're proportional, we have to read between the lines and see that's their assumption, and also that's the way that we're going to have to solve this problem. Now, if they assume it's proportional, they think they figured out how many there are, and then later they have evidence to suggest that they were wrong, then maybe that means that assumption was wrong. That's all part of sampling. But that's last chapter. This chapter, we're just going to assume it and try to figure it out. So before Wednesday, you might kind of look through everything and decide, what do I really need to ask about before we start working on our test? We're just going to have time to go over stuff. And if you're watching this video, hi, and you have things you want me to go over, send me an email.